start. So this is our plan for today. Copy it up here. So midterm. Discussing the midterm. Redistributing the homework. Questions about projects. And then we'll start talking about using floating point working. Okay, so that's the plan for today. So the next thing is, this is the homework that you guys have done. Ellie, could you give this to people? And if you didn't turn in your assignment, just make sure she doesn't give you one to grade. So that's the homework. Meanwhile, I'm going to hand back the exams, which will obviously take a couple of minutes. And to avoid accidentally giving somebody an exam that isn't theirs, unless I'm 100,000% sure of your name, I will call out your name. And even then, I might anyways. So it'd be really bad to give somebody else's exam. So Camille, here you are. David Bitself. Dan Cantor. Kari. I think this is yours. There's no name on it. There's a small one. Peter Clark. Here. Tyler Cooper. Allison. Let's put this on your desk. Ryan Dingman. Nicholas Burkert. James Hart. Yep. Emily Kirkman. Stephen Krieger. Susan Massey. Joseph Maranti. Brett Nakashima. David Rund. Michael Rutherford. Ashley Saunders. Michael Schmitz. Andreas Seekin. Tricia Smith. Scott Terry. Igor. Okay, so that's all the exams. The average score was 3.7 out of 4. And here's your. No, or you give you back your midterm. Your midterm. Okay. So I will briefly go over the midterm, though only briefly. So regarding open source, actually let me pull the midterm up on the screen. So here are the problems. The first problem asked about which programs were open source or not open source as defined by the Open Source Initiative. And let's see, so Magma isn't, Python is, Internet Explorer is not, Perl is, Apache Web Server is, GNU plot's a little bit funny because it is not, its license is its own custom license, and that license isn't officially approved by the OSI. However, if you read carefully about the OSI rules for a license to be approved, it looks like GNU plot's license would be approved.
No.
Yeah, they actually do allow redistribution as patches. Because of that ambiguity, I didn't, no matter what you said on this problem, I didn't take off any points for that. So you don't have to argue too much with me about that. But on the OSI website, they do say that it's the stupid constraint that GNU plot makes. I mean, they'll explicitly say that. But in GNU plot, you can't change the source and and redistribute the modified sources. But if you take the original sources and a bunch of patch files, you can redistribute that. And the OSI license rules allow for that possibility. Nonetheless, it's still not OSI approved because its license hasn't gone through that process. But I didn't take off any points in any case for this because it's so ambiguous. MATLAB is commercial and closed source. Maple is not OSI approved. The Firefox web browser is, and Opera is closed source. So there were 4 that were clearly okay. For Sudoku, it says figure out how to use Sage to solve this. Some people wrote an entire Sudoku solver. One person did. Some people typed SU tab key in Sage and found that there's a Sudoku command. And then one person just decided to write a Sudoku solver that was 100 times faster than mine. That's in Sage. So that'd be Tom in the back. So those were all valid solutions. Yeah, so I think like this puzzle took a couple of seconds to solve with the one that's built into Sage because it uses a pretty stupid algorithm. And so Tom implemented a much, much better one, built on top of somebody else's exact coverings code, which did it in about 1/10 of a second, or less, right?
11.
Yeah.
Is it going to be included with Sage?
Yeah, certainly. Then there was another question that wasn't quite worded correctly, but it was just, if you change the puzzle slightly by moving the one from the middle to the upper left, does it still have a solution? And the answer is yes, it does. So it's easy to prove that it does by just writing it down. Emily and Susan? Are you Susan? Oh, yeah, I gave it to you last time, of course. So so the Sudoku puzzle was solvable just by typing SU tab. So the rough estimates one, this is of course a complicated problem, and there were a very wide range of answers, and probably most people lost points for these, though I was pretty lenient, I think at least. But there are about half of the people who answered problem A, which was to decide how long it takes to find the determinant of a 10,000 by 10,000 integer matrix with 1-digit entries. A very, very large number of people made a matrix over the ring Z mod 10Z, and then found the determinant of that matrix. So they literally made a 10,000 by 10,000 matrix with entries that lie in this ring, which is a ring of order 10, that's true, and every element of this ring can be represented with a 1-digit integer, but that's not at all what the question's actually asking. The question's asking you to write down some random matrix whose entries are integers, like -4, 2, 3, -7, and then compute the determinant of that matrix as an integer. And an amusing thing is that in Sage right now, if you write down a matrix whose entries are in Z mod 10Z, in this finite ring, so this is called integers of 10 in Sage. It turns out that the algorithm in Sage to compute the determinant over this ring is vastly slower than the algorithm to compute the exact determinant of a matrix over the integers, even though the answer here is just a single digit, whereas here it's some massive number. So in fact, if you wanted to compute a determinant over this ring, it would be better to make the matrix over the integers, compute the determinant, and then reduce it modulo 10 in Sage right now, because there's a very optimized algorithm here and not, here, but not there. Okay, so is it clear what the difference is here? They're really completely different questions. If you ask about matrices with 1 digit that have integer entries, and matrices that have entries in the ring of numbers modulo 10. So it's really just a completely different question. That said, I still give people half credit if they gave a reasonable estimate for the time for entries that are mod 10. The next question asked about computing the prime factorization of a product of two numbers. And a lot of people looked online and discovered that this is related to cracking RSA keys, and then used some time estimates from people cracking similar RSA crypto systems using a number field sieve on a supercomputer. Unfortunately, the question specifically asks about how to do that calculation using Sage 3.0 on a computer with infinite RAM. And Sage doesn't have any implementation of the number field sieve, namely of the algorithm that was used to crack these RSA keys. So if you take a random time from the internet that says that some algorithm takes this long to run, doesn't mean Sage will take that long, because there's no guarantee that Sage has that algorithm implemented. Much better was to take smaller examples like this and do factorizations and then just see how long it takes and try to extrapolate from that. And it will take a very, very, very long time in Sage. Let's just say a very, 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 very long time. I mean, it's a factorization you could reasonably hope to do if you implemented the number field sieve, or if you used the number field sieve. That's just I'm not assuming anyone here knows what that means. It's just some algorithm that's very, very complicated to implement that is not in Sage. So if you had a really good implementation of that, it would be reasonable to do this in a few months probably, but without that, it's completely out of reach in any reasonable amount of time. Also, some people, there's a special factorization algorithm that works when P and Q are very, very close, like P is equal to Q plus 10 or something very, very ridiculously close, because then both of the factors have to be close to the square root of it. And if you use that algorithm, it would do this very quickly, but the thing is that doesn't work here. The only constraint is that P and Q have the same number of digits, which certainly doesn't imply that they're ridiculously close. So one person answered the question that way, and then went on to carefully answer the question the other way, which was a good answer. That was you, I don't know, somebody. I don't remember who.
With the QC? The QC function?
Yeah.
Okay.
Good. So another question, so every single decimal digit of a billion factorial, some smart ass answered it by listing 0 through 9. But yeah, so basically what you do here is try computing 10 to the 5 factorial, 10 to the 6 factorial, 10 to the 7 factorial, 10 to the 8 factorial, and then 10 to the 9th. And you notice that it goes up by a certain amount each time. And you get that, I think it takes like a couple of months or something, but it would, certainly you could do it in Sage if you wanted to.
I ran out of memory though. I tried to.
You have infinite RAM.
I tried to do it in Sage, but in this one you could, right?
Yeah, yeah. On a 64-bit machine, I don't know, you could estimate the number of digits. Yep. You did it in 11 hours? Okay.
Memory then.
Right, well, it's hours to months. So I was okay with answers around hours to months for that. I didn't like answers like, it'll never ever complete. The next question, amazingly, I think over half of the people in here got it wrong. And so here's a basic math question. Is this the same thing as 3 to the power of 20? Yes or no? If you were to write this in school, would these be the same thing? Of course, 3 to the 20 is the same as 3 to the power of 4 to the power of 5. So what happened for a lot of people who were in a hurry, I guess, they ended up doing this tower of exponentiations by typing, or somehow writing 3 to the power of 4 in parentheses, to the power of 5, to the power of 6, to the power of 7. But the way exponents work, if you do 3 to the power of 4, and then raise that to the power of 5, you get 3 to the 20. And that has little to do with 3 to the power of 4 to the 5, which is a much, much bigger number. So about half of people, for some reason, were in a hurry and got confused by that problem. One person, while driving home right after handing in the exam, realized that they had confused that. That said, I still think I gave half credit in some cases if you at least did a good job analyzing the time for doing it with the association wrong. But definitely to get this right, you had to do it with the association correct. And then it's actually pretty hard, because if you just naively type it in, you'll just quickly overflow the exponent that's allowed. However, you're only asked for the last 10 digits, so the goal is really to compute this number modulo 10 to the 10. And there are, well, if you want to compute a to the power of b modulo 10 to the 10, say, what you can do is reduce the exponent modulo Euler 5 10 to the 10. So you could just replace a to the b with a to the b mod 5 10 to the 10. And then recursively you can compute all the other, so you reduce the problem of computing the exponent right here, 4 to the 5 to the 6 to 7 to the 8 to 9, to computing it modulo something easy again. And you just keep reducing that way, and at the end you end up getting the right thing. And about a third of people did that, I think. So, in fact, you could just, it's okay to just reduce mod 10 to the 10, and that will give the same thing because of.
I think it's still too big.
What?
I tried that and it was still too big, so I had to reduce it further for the exponents.
Well, yeah, the thing is you have to take B, which is the whole rest of the tower, and you have to apply the same principle, except to, like, so
Yeah,
B is
I did. And
C to the D, so then you have to apply it to that. So
Yeah.
you keep applying the same idea, and it does work, and it gives you the right answer.
Oh, really?
Yes.
Oh, huh.
Yeah. So, I mean, just think of B, it's just the same problem all over again, right? It's just with one less thing in the tower. So,
Yeah,
it's
because
a little bit
I thought it only allowed like up to like 2 times 10 to the 9 in the exponents. And so like,
2 times. But
so I think 1 like leaked out of that range, but
no,
maybe
you don't need to
it
do
was
it
like-
once and for all. You need only to compute a to the power of this modulo 10 to the 10. So you get to do the arithmetic in the ring integers of 10 to the 10. So you actually do the exponentiation here. If you have a number in here, then you can raise it to an extremely large number. I mean, the basic thing is you never want to type. When you're doing exponentiation, you never, ever, ever want to type never, ever want to type something like 4 to the power of something big mod 10 to the 10. You never, ever want to do that. What you want to do is instead do mod 4 comma 10 to the 10 to make a number mod 10 to the 10 and then raise that to a power. And then you can raise to huge powers, as you can see. So it's just much, much more powerful to take your number and view it as a number modulo, say 10 or a power of 10, and then do the exponentiation. Because then at every step in the exponentiation it can reduce, and you just don't get any large numbers. Does that make any sense? If it doesn't, and you really wish you completely understood that, take a course in elementary number 3, and then you'll understand that really, really well. Okay, so I think that was probably the hardest problem, and the main problem was that actually a lot of people here would not really know much about doing arithmetic mod and the Euler phi function, because this isn't a number theory course. And sometimes I forget that not everybody knows basic number theory really well, for which I apologize, but it's just 1/10 of a point, and you could have looked it up. Okay, so the next one was the next prime after 10 to the 10 to the 7, and most people, I think, did a good job on this problem. The one thing that people got tripped up on is some people tried to estimate the time based on finding the next Mersenne prime via the great internet Mersenne prime search. And this question isn't asking to find some prime number after 10 to the 10 to the 7. It's literally asking to find the next prime after 10 to the 10 to the 7. And that's really, 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 really hard. It'll take an extraordinarily long time to succeed. It's easy to write code to do it, but it would take forever for it to run. Okay, any questions on these timing problems? None of them were really easy. I mean, every single one you had to kind of creatively guess at what the runtime was, and I mean, how should you know unless you really understand the underlying algorithm? So, so it was very, very lenient about how I graded as far as the, whether you said hours or weeks. But the main thing was that you looked at the correct problem. So I hope that you didn't hate problem 3 and found it interesting. Because it was certainly an unusually ambiguous question for an exam. Okay, finally, this one, there are, of course, a whole bunch of different things people could do. And it seemed like, judging by the solutions, people didn't have much trouble beating what was on the web page in pure Python. So I think a lot of people did prime count, I guess counting the number of primes up to n. Since Sage has a built-in command which just calls peri to do it, which is very fast, and the pure Python implementation at that web page is actually quite slow, like ridiculously slow. So a lot of people did that problem. See, one person drew the Mandelbrot sets. A bunch of people also did the one where you compute various sums, a whole bunch of different sums using Python or Cython. And a lot of people got a significant speed up just by switching to Cython and declaring data types. So I think people did pretty well in problem 4. Okay, so that's the exam. If you find that I made any thing that you believe is a mistake on the grading, let me know in office hours after class and I'll take a look at it. I have no desire to misgrade anybody's exams, and I'm human, so probably did mess up once or twice. Yes?
I'm just curious, like, what would you like be opposed to, like, what algorithm this problem would be?
So the first one, 10,000 by 10,000, a couple of people actually did that, and it took about just under 2 hours, right? Tom, you did it, for example. Part A takes about 2 hours. You actually ran it.
30.
30 hours? No, part A. The determinant took 30 hours?
Yes.
Okay, 30 hours. So on the order of hours. The prime factorization, I think, in Sage would be, I mean, you couldn't do it. It would take beyond your life. The computer would die and all that sort of thing. Take beyond your lifetime. The factorial, I think E just said that that took 13 hours? 11 hours, sorry. Okay, so 30 hours, no reasonable finish, 11 hours, essentially instantaneous, if you could the right algorithm, and this would take forever. So B and E take forever, and the others literally take on the order of hours. Okay, so in the time you had for the exam, if you would have started clever algorithms, 3 of them would have finished, and 2 would have not finished. And if you put, say, weeks for like problem C, and I marked it wrong, then talk to me, because I think weeks is a reasonable estimate. Just because I really wanted a reasonable ballpark that wasn't completely off. But for example, if you said it would take years to do D, then that wasn't so good, because you can certainly do D pretty quickly. I bet Bernoulli could do D by hand. So don't worry about that. Okay. Did anybody not get their midterm back? What's your name? Dan. Okay. I think I have it here.
You'll make the problem more ambiguous by asking how long we thought Bernoulli would need for each of the problems.
Okay, so now we're done with the midterm. Does everybody have a copy of the new homework assignment? Who wants a copy? You don't? Okay, so here they are, I think. Actually, there's a lot of them. So these are the homework assignments that are due in 1 week. Remember, again, you can drop 2 homework assignments. Okay, so it's homework. Let's see, general questions about your projects. So it seems to me a couple of people have asked about drawing multiple edges when plotting graphs. So, who here is interested in fixing plotting of graphs so that you get multiple edges? So you are. Are you the only one? Emily is. Jim is. Robert is. Okay, who in the class? So Emily and you. All right. So you get dibs on it. How's that sound? Okay. So you can work on polishing up graph plotting. Okay. And Emily, if you want to give her any hints.
Yeah, I can tell you how to do it.
And then if it's too easy, you could do a little more and make it fancier or something to make it feel like a full project. Okay?
Actually, I can give you more requests. So I think it's too easy. Okay, well, I'll talk to you. All right.
Excellent. Okay, good. So that settles that. Okay, any general questions or specific questions about projects that you're working on? Especially questions that might benefit from everyone in the class hearing about them. Okay? All right, so now we're on to floating point arithmetic, which, this is kind of like half a lecture, and then there'll be another half of a lecture on Friday on the same topic, where so I guess it's a big switch of gears, I think, but this is what we're talking about now. And I'm basically going to divide this lecture in two conceptually. So the main focus today and at the beginning of class on Friday is going to be about the really plethora of different floating point models and implementations in Sage. I think Sage literally has more different ways, completely different implementations of floating point arithmetic than any other computer algebra system there is. Hands down. I mean, way more than any system I know of. So unless I just don't know something, there's just a lot of different options in Sage, which of course can be daunting. And each model has its pros and its cons. So I'm going to primarily, my goal today and at the beginning next time is just to give you a sense of what each of the different models are. By models, I just mean literally like ways of computing with floating point numbers, real and complex floating point numbers. What some of the trade-offs are speed-wise, etc., with each of these different models. So it's very much a user's point of view on how to actually use floating point numbers in Sage. Another kind of very important aspect to floating point numbers in Sage is really just kind of basic background in numerical analysis and much more simply just floating point. What is floating point arithmetic? So there's the user point of view, which is just what is there to use, and then there's what is floating point anyways. I mean, so I guess I'll say something for about 5 minutes before we get started here, just about what floating point is. What's your name? I want to give you your exam. Susan?
Oh, Susan.
Yeah. So at an extremely high level of detail, and this is what I want to go into more detail next time about. If you want to compute with floating point numbers to some fixed precision, so think, for example, you want to compute with numbers that are, you have a decimal, and then you have digits after the decimal, and then maybe some base to the power of some exponent. So kind of like what you do when you use a scientific calculator, like an old-fashioned scientific calculator or MATLAB or whatever. You have all these floating point numbers. There's a maximum possible exponent that you can have, and you only keep track of a certain number of digits here. And these digits are all between, the digits are all between 0 and 9. So, and the exponent, say maybe it's up to about 300 and down to about minus 300. So there's just a finite number of these different floating point numbers. So you imagine you're computing with the real numbers, but of course behind the scenes, to a mathematician at least, you can kind of imagine just, since 5 is about the same as any other finite number, if you kind of think about doing things from the point of view of mathematics, from the point of view of finite versus infinite, 1 billion different objects or 100 billion different objects is about the same as 5. You're just going to kind of think from a distance. So these are, let's say, all the different floating point numbers that you can represent in your computer to a given fixed precision. And now you decide you want to do arithmetic. So you take this number, or actually, really you take some number like pi, so it's here, and then you approximate it by one of these numbers, and you take some other number like, I don't know, e, and which is maybe, I guess, here, you take e, and you maybe approximate it by some other floating point number, and then you do some arithmetic, so you maybe take this number and that number, and you multiply them, and you get something over here, but then you have to approximate it because you only have 6 different numbers in your computer. So you do arithmetic, and every single time you do an arithmetic operation, you really throw away a bunch of information, and you end up just approximating by one of these 6 possible floating point values. As you might imagine, if you were to do this for a while in any real calculation, it's completely possible that various rounding errors would occur, and your answer might be completely meaningless. And this is the sort of thing you have to worry about a huge amount when doing floating point computations. And various strategies for addressing this problem are increasing the number of different floating point values that you have. I replaced the 2 by 100 or something like that. Increasing the exponent, that can help. Because basically you're just making it so there are more floating point values that you stored in your computer at the expense of slowing down all of your calculations. That's one technique. Another possibly complementary technique is to use interval arithmetic, where every single time you do a calculation, instead of just rounding to the nearest, or doing some sort of rounding from the actual answer to one of the numbers that you can store in your computer, you compute an interval between two of these numbers that you can store in your computer where the answer actually lies. So throughout every step of the computation, you're always keeping track of these intervals. And then at the end of the calculation, the answer is not a specific floating point number, it's two floating point numbers, and you are guaranteed that whatever sequence of arithmetic operations you did produced a number that lies in that interval. If the interval is really, really small enough for your application, you're happy and you're done. Otherwise, you basically redo the whole calculation, but with higher precision, that is, with more possible values so that the intervals will be smaller at the end. So that's another complementary approach. And that's what we're going to mainly talk about in class on Friday, is ways of dealing with the fact that you lose precision. And of course, there are whole classes, several classes that are taught at UW on numerical analysis, which given assumptions about how arithmetic is implemented in a computer, and there are these IEEE standards that specify exactly what sort of rounding behavior you have and what sort of errors are allowable, then given those assumptions, if you run a certain algorithm and your input has a certain sort of tolerance, then the output will have a certain tolerance. So there's a lot of theory there, and that's not what I'm going to talk about too much, but I'm going to tell you what sort of tools are available in Sage for addressing numerical problems. So first, here's a list of a whole bunch of different kind of monikers, or data types really, or fields that correspond to different ways of computing with floating point numbers in Sage. I'll copy over here on the blackboard. So there's float. This is a built-in Python data type. Every copy of Python includes a data type called float. This wraps machine doubles. It's really like the double type in C, and so you don't have very much. Basically, you have 53 bits of precision, and your exponent can't be too big. So you have float, you have complex. This is just like float, except you have a pair of these things, and then you have arithmetic. It models complex numbers. And you have decimal. This is another type built into Python. So these are three Python data types, and they're native. Every copy of Python, since I think Python 2.3 includes all of these.
What does decimal mean?
I'll get to that in a minute, but decimal is a data type built into Python again for computing with decimal numbers in base 10. And it allows arbitrary precision numbers, and it's kind of aimed at, the claim is that it's aimed at financial applications. So it does like grade school arithmetic with base 10 numbers. It's not fast at all, and it has nothing to do with any IEEE specifications or anything.
But the actual calculations must be made in base 2, is that?
Why?
What's that?
Why do they have to be done in base 2? You could program a computer to do high school multiplication and addition. You can. And that's what this guy from Central America did. And he wrote this Python. I actually sat next to the guy that implemented this at PyCon 2005. And he's a nice guy. I don't like the decimal module very much, but he's a nice guy. He literally implemented all the arithmetic in base 10. You can do it, it's just slow. But it makes banks happy, I guess. I don't know. I mean, it is what it is, and we will in fact play around with it in just a second. Then we have RDF, CDF, RQDF. These are all types that various people put a lot of effort into implementing for Sage. RDF and CDF, these are acronyms for real double field and complex double field. They're very, very similar in spirit and underlying representation to float and complex. The difference is that these are Sage types. They only come with Sage. And they play much more nicely with the rest of Sage. For example, you can make a matrix whose entries are RDF elements in Sage, and then you can call various commands like LU factorization on that matrix, and it will very, very efficiently give you an LU factorization. Or you can make a polynomial whose coefficients are in the real double field in Sage, and then do arithmetic with it, and find roots of the polynomial and so on. So that's the sort of thing you cannot do with floats or complex. So Sage doesn't support arithmetic Sage doesn't support arithmetic, like a lot of the higher level arithmetic over these types. It only supports these sorts of types. Actually, RDF itself is a ring. It's the real double field. It's a field, so it's an object. It's not a data type, but its elements have some type. Real quad double field is, it's like real double field where you take 4 doubles in a row, and you define addition and multiplication where you store your numbers as a list in memory of 4 doubles. This is something that
Is the word field used appropriately? I mean, the.
It models a
complex
field.
Then they're not fields, actually.
in the sense of mathematics,
I mean,
they're not
They're
fields.
often
Well,
slow and complex, they're actually not fields.
so there's an abstraction.
They fail lots of the rules, like associativity and things like that.
So, yes, they are not fields in the
So
sense
what
of
is the
mathematics. They,
argument?
however, model fields. But I mean, you could also argue that ZZ in Sage, the integers in Sage, is not a ring because it's actually finite in a computer because your computer has finite memory,
Yeah.
etc. So, I mean, every single object in a computer is sort of finite. But so RDF is it's an object which is called a real double field. It's an abstraction that models the idea of the real field, but the specific model is not a field. I mean, it's a collection of double precision numbers. So it certainly, if you take the actual elements, then it fails all the field. I mean, it fails all kinds of field axioms. Yeah. But real life deal with it. So real quad double field is another field, which is popular with people doing really distributed computation. And then there's CC and RR. So these are very, very interesting. And what they are is they give you arbitrary precision real numbers and complex numbers. So you can specify, I'd like to do arithmetic with 10,000 bits of precision real numbers. And that's what you get here. And the really, really cool thing about these, which are built on top of a library called MPFR, is that they're platform independent. Their behavior is identical whether you run them on a 32-bit machine or a 64-bit machine or a PowerPC or an Intel processor or whatever. And that is extremely rare if you look at all the other sort of floating point models that you find in Sage or in computers in general, how that sort of system independence. For example, if you look at the Python manual, here's what they say about their floats. Floating point numbers are implemented using double and seek. All bets on their precision are off unless you happen to know the machine you are working with. So that does not exactly inspire confidence. It does make you think it's probably going to be pretty fast. I mean, C doubles, it's got to be fast. However, when they say all bets are off unless you know the machine you're working on, and you think about writing a Python program that's going to be run by all kinds of people on random computers, it's worrisome. And that's how it is. That's how Python floats are. If you use Sage and you use RR or CC, which are built on MPFR, so let's put it over here, built on MPFR, then these are guaranteed, assuming that there isn't a hardware bug in the computer, to behave identically on every machine you run them on. So the rounding, everything's going to be exactly the same no matter what. There's also a couple of integral arithmetic fields, RIF and CIF. So these are also native types in Sage, and they allow you to do arithmetic with real intervals and also with complex, I think complex intervals are rectangles, but I haven't actually used this type. It's pretty recent, so I'm not sure what it actually is. We will soon find out. But these allow you to do interval arithmetic. And they're very optimized, and they were very, very carefully implemented by Carl Lee. So they're quite nice. And I don't know of any other general computer algebra system that has really, really optimized interval arithmetic. I mean, you can implement your own kind of cheesy interval arithmetic in an afternoon in any computer algebra system that has real numbers, but to implement something that's really, really fast and that implements a lot of special functions like the sine function on intervals, etc., that's much, much harder. And this is built just like the reals and complexes here are built on MPFR. This is built on a library, the C library, called MPFI, multi-precision floating intervals. Maybe it's yeah, it's MPFI. And so what we did was we took this library, we wrapped it using Python, and then provided a nice interface, extra functionality, found several bugs. For example, I remember there was an interval that came up where when you tried to compute cosine of the interval, it would hang forever because of some mistake in the C library. So we found bugs, fixed bugs, and that's the resulting line. That's what we have. So, so there you are. And every single thing that Sage uses for floating point arithmetic is a wrapper written in Python on top of an existing C or C++ library. In fact, this is the only one that's C++. The others are all C libraries. And oh, and there's also there's even more available that I haven't listed here yet. So Paris, this number theory library, it has its own arbitrary precision floating point number implementation. It's completely separate from MPFR, it's separate from what Python has, etc. So it's yet another completely separate arbitrary precision floating point arithmetic implementation. And it's available as well. And so you have yet another possibility available there. The main interesting thing about Paris arbitrary precision numbers is they also have a very, very wide range of special functions, like say the gamma function or the Riemann zeta function or the incomplete gamma function or the error function, all these sort of special functions that are in, say, Abramovich and Stein and that sort of thing. So they're really important. It has them such that they can be computed for an arbitrary complex input to high precision. So that's one thing that Paris offers. And I think it has a wider range of arbitrary precision special functions than any other open source program. So it's kind of one of the special unusual things about Paris. So for Sage, when you say want to compute a complex special function to high precision, what it does is it turns the complex number that's represented using MPFR into a Paris complex number to high precision, does the special function there, and then converts back, unfortunately. But the thing with Paris is it depends, the behavior of the Paris floating point numbers, unlike MPFR, depends on which machine you build Paris on. And it often depends on which version of Paris you're using. So in fact, it changes a lot from version to version. So we took to, I think most recently we took to just not printing the last couple of digits of the output of Paris numbers, since we had to change all of our examples every time we upgraded Paris, because they kept changing back and forth. Okay, so that's the general overview. And now I'm going to give you some specific illustrations into each of these. Of course, since I only have a few minutes left, I'll only get to talk probably about the Python ones. So, first, to make the type of a Python float is float. And again, just to emphasize this, this is not an arbitrary precision type. It's just C doubles. So, for example, if you try to do, float, and then you type in your really big number with all its important lower order digits, then they just disappear instantaneously. So you're not going to get arbitrary precision floats from this. Here's a little benchmark. We'll take a float, just give us a sense of how fast Python floats are. And what we do is square that float 1 million times. And it looks like it takes 0.26 seconds. So it's just kind of a sanity check. If you had a basic arithmetic type, like anything listed there, and squaring 1 million times, say, takes an hour, there's a big problem. So this is something to keep in the back of your mind. If it's taking under a second, there's probably not some huge issue with the arithmetic. If you look at Sage from, say, a year and a half ago, some of these types were under the hood implemented, especially CC, for example, were under the hood implemented in pure Python. And they were very, very slow. So literally, if you wanted to do that benchmark, it could take a couple of minutes or more, maybe a couple of hours even. So it's a good sanity check that that sort of thing doesn't take too long. And Python itself is very, very optimized for its own basic numerical types. So of all the benchmarks, when we do it, that's going to be probably the fastest, or almost the fastest. Of course, we could do it in Python and probably be way faster. We just have to make sure the compiler doesn't optimize it away. I'm right now implementing a Python version of that benchmark with C doubles, so you can see what sort of overhead there is. I'm going to do it slightly differently to make sure that the compiler doesn't just optimize everything away. So notice what I did here was B equals, that's going to be bad because it'll overflow. Maybe I'll do that. You never know. Well, I don't want the compiler to just say, hey, I can do that once and I don't need to do it again. How about plus n? Yeah, probably the compiler won't optimize that out. Yeah, that's pretty fast. So let me just up this by one more to make sure it's really doing the loop. Yeah, so it's really doing the loop. So the speed penalty for using a Python float over a C double is something like only a factor of 20 in this benchmark. I say 20 because the time here is about 10 times, a little more than 10 times better, but we're doing 2 arithmetic operations. So something like it. It's not really that bad, only 20, but of course that's still significant. Okay, so here's one of the first things. If you take a Python float and raise it to a big power, even 300, you get an overflow, which is kind of annoying. So it doesn't take too much for C doubles to overflow. And this can actually be a problem in everyday, well, maybe not for you, but it's been a problem for me. It was most recently a problem when I was implementing the algorithm for computing the determinant of an integer matrix. In order to do that, in that algorithm, you have to compute a bound on the size of the determinant. So what you do is you compute a bound on the number of digits, but intermediate steps in computing that bound end up involving floating point numbers that are a bit bigger than this. And it just overflows if you use C doubles. So what you could do is use MPFR. These work with 53 bits of precision. They work almost exactly the same as machine doubles. However, they allow the exponent to be just absolutely horrendous. I mean, you can make really, 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 really large exponents. It just doesn't have the constraint that the exponent is small. So you just switch to using them, and it's a little tiny bit slower, but it works. So there's shortcomings to using floats. But in Sage, I mean, you have a lot of other options. So if I were to do, say, RR of A, AA, then I get that, and then I can do AA to the power of that, no problem. Okay, so I'll continue talking about the other data types first thing on Friday, and I'll also, in particular, say some things about interval arithmetic. Okay? And also using